Hey everybody, this is the second part of your earthquakes notes. Now we're past the point where we talk about, what an earthquake is and secondary effects of earthquake and stuff like that. And now we're going to start learning how to locate, at least find the distance to an earthquake and when an earthquake began. So we have to take a trip down memory lane here. It's all going to deal with the seismic waves, and that's why we have to start talking about seismic waves again. Okay, so seismic waves, there's three types that exist. They're called the P waves, primary waves, S waves, which are the secondary waves, and the surface waves. Okay, and just like it says here in the notes, P waves, S waves, and surface waves are all called seismic waves because they're vibrational waves. That's what they are. The seismic waves kind of shake things. They can help us see inside the earth, so we can see the thickness, of interior layers like we learned before. They can help us locate the distance to an epicenter, that is how far a location is from the epicenter of a quake. Figure out when an earthquake began, we call that origin time. Measure the strength of an earthquake on the Richter scale, like a 1, a 2, a 3, and so on, and even identify for us what the Earth's interior is made of. Like, is it solid? Is it kind of liquidy? Is it molten tea? All the stuff that we kind of did, a few weeks ago of Earth's interior layers. So that's what the seismic waves are going to do for us. They're also the vibrational waves generated by an earthquake that cause massive destruction. Both P and S waves, all right, they're going to leave the focus and they're going to travel towards the surface, not the surface waves. Surface waves are a combination of P and S waves when they get to the surface. So both P and S waves leave the focus at the same time and travel in all directions. Some make it to the surface and some travel towards the core, of course. Okay, so a seismograph, once again, is just a piece of machinery that records the seismic waves on a seismogram. And the seismogram is just this piece of paper that's traveling through the seismograph. And what you're going to see is the first blip to arrive, that's the P wave. Okay? And they're real short usually, too. And then the second blip to arrive, and these are going to be taller waves, are the S waves. And I want you guys to notice this thing right here. This is called the time gap. And that is the difference in arrival time of the first P wave and the first S wave. When we can find out how much time it has been since those two waves arrived, we can find the distance to an earthquake. And we're going to be doing that in today's activity in a little bit. And these are the surface waves over here. They're the third blip to arrive. So P waves are first, secondary waves are second, surface waves are third. And they're much stronger because the surface waves are these two added together right here. And the surface waves are what cause all the destruction of the quake. And we monitor how tall they are on the seismogram to see how strong the earthquake was. So just like it says right here, it's a piece of machinery that records seismic waves on the seismogram. Okay, an example of a seismograph, of course, is called the Richter scale that measures when P waves and S waves and surface waves arrive. The seismogram shows us the strength and magnitude of the quake. From the seismogram, we can also tell how far a location is from an earthquake and what time the earthquake actually began. We're going to be doing this later on. All right, so a little bit of review of P waves. P waves stand for primary wave because it's the first to arrive at the seismograph. Now they move Earth side to side, just like Ariana Grande's song. That's how they move it. They're not real destructive. They tend to be the least destructive. They don't cause a lot of devastation on the surface. They travel the quickest. They can move through all materials. They even move through gas, which makes a little rumble noise, because the gas of the atmosphere, which makes a little rumble noise of an earthquake. The S wave stands for secondary wave because it's the second to arrive. It's going to move the Earth instead of side to side. It's going to move it up and down, so a little more destructive. All right, they travel the second fastest. Remember, they will not go through the outer core because it's liquid. They don't go through liquids, and they're slightly taller than the P wave on the seismogram. The surface wave, sometimes it's also known as the love wave, actually. Okay, they're a combo of P and S waves added together at Earth's surface. These are the most destructive. And instead of moving the Earth side to side or up and down, they do both. They move the Earth side, up, down, side, up, down. It's more or less described, like major earthquakes are described, as the surface of the Earth looks like an ocean wave. If you can imagine that. I can't. I've never been in an earthquake before, but that's how people who have survived earthquakes describe it. Notice the height of these waves are used to find the strength of the quake on the Richter scale. The Richter scale, guys, goes from 0, which basically is nothing, no earthquake, up to a 10. And in theory, an earthquake of a 10 is absolutely impossible. A 10 would be such a strong quake that it would split Earth into two. All right. The strongest quake ever recorded to date was from 1960, and that was a 9.4 on the Richter scale. They don't get much stronger than that. The Indonesia earthquake of 2004 was right there around 9.1, 9.2 on the Richter scale. When it gets to be so strong, it's really, really hard to even get an accurate number on the Richter scale. Okay, now here's what you're going to be doing in your homework, and I put a link to these notes in your homework. Okay, the first thing you're going to do is how to find the distance to an earthquake from a location on Earth. That is how far to the epicenter. Okay, first thing you want to do is record the arrival time of the first P wave, and I've put that in for you. So let's say the first P wave arrived at 1:18 and 40 seconds, and that is called PA, P wave arrival time. And then you want to record the arrival time of the first S wave. So here's my first S wave arrival time, 1:21 and 30 seconds. Okay, now, big thing you have to do, you have to find the difference in arrival time of the first P and S wave. And this is called always the time gap. So you'll hear me say time gap, time gap. Okay, so how you do that to find the time gap, you take SA, that is the S wave arrival, and you subtract PA, and that is P wave arrival. So I'm going to subtract SA minus PA. And I've done it down here for you, so you can see how I'm doing it. Okay, and your difference is 2 minutes and 50 seconds. And then you're going to look at your graph and you're going to find the distance, which is this. So right here, I found 2 minutes and 50 seconds. So I'm going to go out, just like the arrows are showing you, until I hit my line, my time gap line, and drop it down. And right there is my distance of 1800. Now, notice, guys, when you're doing this, how you subtract time. Here I have 1:21:30 minus 1:18:40. You got to group it together, okay? So for example, right here, I have 40 seconds from 30. I can't do that. So instead, I'm going to cross out this 30, and I'm going to go borrow a minute. So I cross out 21, and I make it 20 minutes. Now remember, 1 minute is how many seconds? 60. So what I'm going to do is add 60 seconds to this column. So if I had 30, and I add 60 to it, now I'm at 90. Now can I take 40 from 90? Sure. So 90 minus 40 is 50. And then this is now 20 because I borrowed a minute, so 21 became 20. And 20 minus 18 is 2. This is a little funky, but this is the best way I found to subtract time. And then 1 minus 1 here, don't have to worry about that. So that's where I got my time gap of 2 minutes and 50 seconds. And then I just went to my time gap on the y-axis here, and then go out to the line and down. And this is a nicer time gap graph for your classwork. So you'll see it's time gap versus distance. So the time gap is on the y, and the distance is on the x. So once again, like 250, you just kind of find about 2 minutes and 50 seconds here, and then you go out to hit the line, and then you drop it straight down. And that's what you're going to do. And we're just going to do as best as we possibly can here, because I know that you don't have to print this stuff out, all right? Now, the next thing you're going to do is find origin time. Origin time is when the quake began, and that's kind of important too. We're finding epicenter distance because we want to see where all the destruction is going to be, but origin time is like, we need to find out what time it began so that we can kind of think about where we're going to find most people. If it happened in the middle of the night, if it happened first thing in the morning, this is very important. It's not as important as finding epicenter distance, but it is important. So how to find origin time? You're going to find the distance the location is to the earthquake epicenter. That was from the previous lesson, okay, or the previous thing we just did. You need to find the P wave travel time for that distance, and I'll show you. And then you're going to subtract the P wave travel time on a seismograph from below. Okay, so what I'm going to give you is I'm going to give you the arrival time. So let's say the arrival time was 1:18 and 20 seconds. And let's say the distance from the epicenter was 2,000 kilometers. I would have to give you this stuff. What you're going to have to find is P wave travel time. That's called PT. And then you're going to need to subtract PT from arrival time. And that's the origin time. So down here I've shown you, it says 2,000 kilometers. Okay, so what I'm going to do is I'm going to find 2,000 kilometers on this graph. And I'm going to go up until I hit the P wave line. You've seen this graph before. Okay, and then I'm going to go over and read the y-intercept, which says 4 minutes. And that you can see right here. So what I did was I gave you this information. That information was given. And then I found 4 minutes. And now all I'm going to do is subtract PT from PA. So there's PA, 118.20, minus PT, which is 4 minutes. So 118.20 minus 4 minutes is 114 and 20 seconds. And here's a nicer graph for you. Nice and big. All right, and there's your P wave line again. And you're just going to be finding the distance and then going up and reading the y-intercept. Finding the distance, going up, in this case it's 7 minutes. So 6,000 kilometers I go up, and that would be about 9 minutes and 20 seconds. Or 3,000 kilometers go up, that would be about 5 minutes and 40 seconds. Last thing about the Richter scale, we're going to do some more work on the Richter scale next week, and then we'll be done with earthquakes. But the Richter scale, it measures the strength or magnitude of a quake. All right, remember, it uses a range from 0 to 10, although once again, 10 is theoretically impossible. Strongest quake ever recorded was a 9.4 in 1960. All right, and that was Valdivia, Chile. All right, caused a massive tsunami. This is a logarithmic scale. It means that every number on the scale does not differ by 1, rather by 10. Okay, so this means that each step on the scale increases in strength of 10. So example, a 3 on the Richter scale is not 1 time stronger than a 2, it's 10 times stronger than a 2. So just like your reader you just had on the Japan earthquake, the Japan earthquake was 3 numbers higher than the Haiti earthquake. And therefore, because it's 3 numbers higher, it's not 3 times stronger, it's 10 to the third. 10 times 10 times 10 times stronger, 1,000 times stronger. All right, that's a lot. So a 3 on the Richter scale is not 1 time stronger than a 2, it's 10 times stronger. And just think about, strength, guys. Think about if you were 10 times stronger than me. None of you are. Some of you are a lot stronger than me, but no one's 10 times stronger than me. All right, that means if I could bench a measly 100 pounds on the bench press, you could bench, if you were 10 times stronger than me, you could bench press 1,000 pounds. And I guarantee none of you can. I know some of you are very, very strong, but no one's benching 1,000 pounds. All right, that would be an earthquake that's one step different. And then we're going to do this for next week, okay? And I'll describe that real quick, and then you guys are going to do this portion next week. But for this week, you are going to be finding PT, origin time, right here. You're going to be doing this, number 5. You're going to be doing number 4. And you're also, you're going to be being asked some questions about seismic waves right here. And I put a link to these notes right here into your homework so it can help you out. All right, have a great week. All right, miss you guys. Take good care.